Hello everyone, welcome back to this tutorial series showing you how to make the Helix Bridge in Grasshopper. Last time we ended with creating the deck for our bridge, and this time we're going to focus on creating the base, which we'll call the pylons or the columns, however we name it, which are these big structure that supports the bridge, and there are 4 of these in total. And as you can see, they connect to the underside of the underbelly of the bridge in 5 points. 1, 2, 3, that one down there, and 5. And they all come back to this cylindrical base, I would say, and that is sits within this what looks could be maybe concrete. I'm not sure, but we can also create this one as a whole package. Um, and then we'll see how far we can go. Maybe we can also pick up these viewing pods, but we'll see about that. Okay, so let's get back to the script. From the previous video, I simply gave all of these clusters basically a group with a nice color. So this is what we did last time. That's our deck. And let's focus on the bridge. As I mentioned before, we needed the points, and if you hadn't noticed, all these points sits just below your deck, so we can start from there. Okay, let's see, what do we need? The first thing we need is obviously the 2 helix curves, because that's where the points intersect. So let's come here, and I found this is the big one. So what we can do is already come in here and just create an output parameter for ourselves, and we just call this what's it called here, outer helix. Okay, so we could just call this outer helix curves, something like that. We do want to show the text. I'm going to add it to the group, create one more, and give it to the inner helix. And then what we can do is just come over here, make a copy, set it to hidden. Oh, I don't want to copy. Oh boy. Set this to hit. Oh, I don't think I've copied it. Okay, now I've got these 2, and basically now what I can do is just take all these, make another copy, because I want to use these as just places where I can just take it and copy it away. And this is what I've done here. So as you can confirm, that's the major, and this is the inner. Okay, I can hide. Oh, hide these. Okay, now that we have this, let's see. To get the point where they intersect, we can simply use, if we come over here to intersection, physical curve to curve. One thing you should pay in mind is these are per curve is wrapped up in its own branch. So you probably have to graph one of the leave one of these grafted, because they're essentially grafted, or you can use one of these flattened. So let's plug in and see what's going on. We have points, although the points only in one direction or in one place, which is the bottom one. Well, actually they shift. You see, some of those are actually somewhere else, and that's because the grafting tree structure that we have here. So we just have to make some sort of coin toss, basically. So let's say we want the outer helix to be nice and clean in its own branch, but we want the inner ones to be grafted. Actually, let's simplify both so that they look nice on the input, and just flatten one of the A or B. So when you've done that, you're basically saying each of these curves will try to clash with all these, and second of that will clash with all these, and so on and so forth. What that gives us is a lot of points where they intersect, as you can see on my screen, and that's exactly what we want. One thing I do want to check is for this you might need the Kangaroo 2 plugin, which I have this one. they have this very nice component called remove duplicate points, which I can use to check for duplicate points. What I do is flatten the P and just send everything in, look for the amount of points I have prior calling the duplicates, which is 128, and the output is 128. That means I have no duplicate points, just to make sure. So once you've done that, we can start filtering out the points, because what we saw in the image is the points that are on the same level of the deck is not needed for operation. So we need to find a way to call that away. And if I look from the side, which side is better? This side, I think, could provide more information. Yeah. So if I look from the side, what we want to do is basically say, get rid of the old one. What we want to do is, I only want the points that are here. So basically, the most bottom and the second most bottom. So the top points I don't want, right? What I propose that we can do is use a logic that takes the the z values of all these points, right? These 1, 2, 3 heights, and say if you are this high or higher, I don't want you. Everything else, I want. Maybe something like that could work. So let's try that. Okay, but first we need to deconstruct a point in order to get our z value. So we can do deconstruct point, which I don't see it yet. Deconstruct point, there we go. And let's put a panel here to view the z values. Oh, interesting. Okay. Oh yeah, of course, this is the midpoints. Got a little bit confused there. And the next thing we want to do is let's make a sort function, because we need to sort these points anyway. So the sort thing goes to k, which only accept numerical values, and the synchronized sorting will be the points. And what we get here is, I think, the most bottom points. If I look at the sorting of this, okay, so it looks to me that the midpoints are going to be, so the most bottom points are obviously the lowest z, which is negative 5.4, but the top points is 2.7. So what can we do? We can try to make a domain out of these values. So we could say bounds, and what that does is it takes whatever value you give it to it and try to wrap the outermost let's flatten this for now because we only need one bound, and try to make a domain out of it that encompasses all these numbers that we have in the z value, which is the lowest being minus 5.4, highest being 2.7, minus 2.7. And what I can do with that is perhaps remap it to another range, because as you may know, the sort values sorts the negative value being the very bottom. Actually, but what we want is actually the 0.4 to be on the top, right? You can say we can just flip this around, but what happens if your bridge doesn't sit where the z value is negative? Let's say where it's all positive, then you're calling the wrong points, perhaps. Then you're calling the most bottom one, when in positive perspective, the most bottom point is actually the highest. So let's get rid of that confusion by just remapping it. Basically, what I want to do is turn these negative values, or whatever values we give it, into a more unitized list. And you'll see what I mean by if I use the remap component, I'm going to remap all these values that prior to sorting, because it doesn't really matter, and put it into This is the source. So if I take two side by side, actually I want that side by side, and I give it here. Okay. So what you see is remember the 2.7 is actually the highest, right? And whatever's lowest, let's see if I can find is so the second tree has exactly that example. So let me visualize that again by drawing it. Let's consider this point. Let's consider this point, that point, and that point. We know the z-value of the top point is minus 2.7. This one is 4.6, I believe, but the bottom one is minus 5.4, right? After our sorting process, after a remapping process, what has become of our points? We look at these two trees. That's not a good color to pick. If you look at two trees, meaning these four values, is 2.7 has become a 1, okay? Has become a 1, and the 5.4 has become a 0. In this sense, we can always say whatever is the top value is going to be the highest because it's a 1. 1 is obviously higher than a 0. And what we can do with this information is we can say, can I undo that? Oh, I can't undo that. What we can say is, hey, whatever's bigger than 1, I don't want it. And what we end up with is all the points that are below 1, in other words, below minus 2.7. So let's put that into the real script and see how that works out. So let's create an evaluation in order to get ourselves some sorting processes. I'm gonna do the formula in the text so we can understand it more. So we can say if, right? Let's close that instead. If x is bigger than 1, or just give it let's give our script a little bit of leeway. 0.99, that's very close to the 1, and we can be sure that with whatever tolerances is built into Rhino, 0.9 is going to be within that tolerance. So we can be sure that the top points will be culled. And we can say if you are bigger than 1 or 99, I don't want you. Else, true, I want you to stay. This is basically what it says here. So we can plug that into the F, plug that into the X, so you don't need the Y. And now what we can do is we can open up a culling pattern. The points we want to cull, we can actually select all the way back here because we haven't done any reorganizing of the tree structure, so it will stay the same. The list we want to modify, the pattern that we want to give it to, and we can close that. And when you select this, you see we only have, is that a point? Oh, that's from here. We will only have the bottom point selected. So that's one way of doing this. And with these components, we've selected the bottom points. And what we want to do with these points is, if you look back to the picture, it starts at a predefined distance, all these. There are two things you can do. I've already know the distance. I measured it, of course. But if you don't believe me, you can measure that yourself. Which is always good to do that yourself and without blindly believing someone else's word, is what I would do. What I found out is it's just going to be a rough sketch. What I did in Google Maps top view is I measured one point there and I drew a lot of lines in order to see where the first pylon is. And what I found out from the start to about somewhere there, the distance is 45 meters. The same goes for the other end. And so this is pylon number 1 and this is pylon number 4 because we have a total of 4, meaning we have 2 somewhere here. And what I found out is they're actually divided. But if you divide this, one of these will not be symmetrical. If you were to divide a bridge into a half, you know, you cannot put two of these like where they should be. Or you can try that. But what I found that there is a small shift between, if you were to divide this here, the other ones will be somewhere here and here. And what I mean by it's not symmetrical is, I think, if I measure that correctly, you can double check that yourself. The distance, oh, this is not proportionate, unfortunately. But what I want to say is the distance between these two here is the same, whilst the middle distance is, I think, slightly larger. Or was it smaller? I'm not sure. Oh, that's a smiley face. But that's what I found out. So what we can start is we can start dividing the first and the last 45 meters and see what we can do with the in between ones later on. So let's do that instead of talking too much. How do we start? Well, we know that it has to be 45 meters from the start and 45 meters from the end. So what we can do is, I would say, I'll actually want to select the most bottom points. So okay, let's deconstruct the points again. And maybe you can do a different kind of sorting for you, is with the lowest point we want to select. We can actually use this instead, or we can just use it as dispatcher. We can just copy and use this basically. We do need some tweaking of the domain, but that's fine. But there's another way we can go about this, is we can see 0.4, which is the last value, right? In here, if you do sort, what do we get? .4 being at the most bottom. So we can actually do a, let's flatten. Yeah, let's flatten this part for now. Then we get the most. How do we subtract all these 5.4? There's one thing we can do, which is called, I think, the member index. Oh, member index. If you read the description of this component, what it does is find the occurrences of a specific number that you supply to it. And what we want to do with this is, I'm going to just take a list item from the first point, because I know that's going to be the lowest point. And I want to say, of all these numbers, the set, wait, what is the S? Set to operate on, I want you to find minus 5.4. And what it outputs, for me at least, is the indices where that number is found. And it found it within the first 26 numbers, because 0 is also counted in. And if you look at our sorting process, we do have 26 of those lower numbers. So with that, we can just do another list item using the indices that we got. And we also need, oh, one thing to not forget is also give that to the synchronized sort, so that it's sorted accordingly, and select that point instead. So now we have all these bottom points selected. Now you may wonder, can't we just use this for this sorting? Yes, you can. If you can find a reliable way to identify that middle Z, which is, I think, minus 4.6667. If you kind of find a reliable way to do that, you're free to do it, of course. I have another, if you want to go that way, there is a component within the same tree set that allows you to do it. I think it's create set. And what this does is it plugs in a lot of numbers, and it just outputs the unique ones. And that will tell you how many unique ones you have. So if I were to come here and where's my Z? That's my Z. So these are the values you want to have evaluated. But if you plug this in here, of course you have to flatten this. What I would expect from this one is three numbers, minus 2.7, minus 4.6, and a minus 5.4. Oh, there's double 2.4. Okay, this is exactly what I was talking about with the 0.99, because the computer sees these two are two distinct numbers, because I think after the comma in the decimal, there is probably a difference in heights. It has to do with the tolerances of the Rhino document. So that's why I always include a small margin for myself in order to help out the computer to distinguish the values that I want them to distinguish. But that using a set is a way to also do it all this that I've done here. It's a matter of experimenting and which one you find more comfortable, that you are well, that you believe your data will be precisely the ones you're looking for. So let's go on with this. What I want to do here is do an interpolated line. Okay. So with this interpolate, oh, well, what happens here? Have I picked up the wrong values? No. I might need to sort this first in order to plug in, because if I do a list point list, let's see, what values am I looking at? Yeah, okay, they're all around. So I need to find a way to sort this out first. Let's see. Well, wait, hold on. There's actually one way we can do this, which is if let's take in an I-beam for that. This might be even more reliable. Uh, what I want with the I-beam is actually just their height, nothing else. Or actually, we can also use them to create our curve. So if we do an interpolated curve, we do we parametrize, we say 0.4, so we get the middle point. We know that these curves are sorted already for us, so we can interpolate a curve like that there, and we can just take 1 point out of those in order to get our z value, which I just hope, I think it's minus 2.7, yeah, just to be sure. So what we can do is the whole reason why I did this, because I want to create a line there so I can sort my start my sorting process. So actually, perhaps we can just stop, not use this. But what I wanted to do is figure out the distance and difference, and just move this line down. You know, we just need this line in order to determine our 45 meters from the start and the bottom, and the end, and create a point there. So let's see how we can do that. We have a z value. Actually, we have a point. What we can do is we have our lowest point here, which is sorted, which is fine. We have a lower point selected from here, which is 5.4. I don't need to select all of it. I'm just going to delete all this. Well, I could just do what's that called? Distance? No, wait, distance works on points. Difference. Let's see what difference give us. The difference is not as reliable as I hoped it would be. This is okay, it's sorted already. Let's see what values they give us. 2.7, which is right. I mean, 5.4 minus 2.7 is 2.7. But still, I'm not comfortable with that. So what I'm gonna do is go into evaluate. I'm gonna plug in I'm just gonna plug in these two values instead, and my formula will be absolute x. Wait, which one is higher? That doesn't matter. Absolute x minus absolute y. This will, the absolute, if you've done math, you know what it means. It turns any values into positive, even positive to positive, but that doesn't do anything. Negative to positive. What I want to do with this value is actually, I want to absolute that too, because in a weird universe, perhaps, you selected the wrong one, you plug in the wrong one, and let's say this becomes that, that becomes this, and what you get is negative. Yeah. But you can say fine, then just make sure you always select the top points, which is doable. But there's another thing you can do is, I want to now move this. I want to move that geometry in the z-axis. And then I'm going to say, well, this has to be a negative. That's the problem, isn't it? Now it's going to move up. You can just say negative that, which is also fine, I guess. But what I'm going to do is just to build in that assurance for myself. I'm going to re-absolute that value, even though it doesn't do anything. And from here, I can say minus x, which is kind of like double work, because you don't need this actually, because you already know it's 2.7. But in the event you chose something wrong, you come here, I don't know, you messed up something. This is just a feature to make sure that it will always and always run right, and you can just forget about it because it will always be right. Okay, looking at the time, I've been talking for half an hour on this one, which we haven't done a lot actually. So what to do? Since we have this here, we might as well continue on, because I would like to continue on actually. So let's do that. But if you need a break, please do so in order to take all this in. Okay, to recap, the reason why we've done this is we want to use this line in order to identify where the columns are. So we can start by saying the 45, okay? The 45, which is start and the distance maybe. And what I want to do with these values is we have a total length. Okay, now we can use the total length. I believe it's this one. Yeah. So we can just drag that. Actually, what I'm gonna do is cut this. I'm gonna paste this in the middle. So we have the total length of that. And what we want to do is we can say, I want you to subtract that length from the twice this length. So I'm gonna do an evaluation that says, you go there, and the formula that you will have is x minus 2 times y, which should get me the distance between 190 meters. This then have to divide this by, what was it? By 3. So let's, we can actually divide it here already. I mean, since we don't really need the 190 value. But what to call this? We know we have to divide by 3. Sections in between. Actually, yeah. I hope that makes sense. I'm gonna give it to a z, and then we can say this whole bunch, I want you to divide by z. Then we have our value. And now we need to combine this. We need to combine it in such a way that we will have first 45, and then the 63 point blah blah blah, and then again, and then I think again, or am I dividing that too much? 1, 2, 3. Oh no, we don't need it, so we don't. And then we have this. No, actually that doesn't make sense. I made an error. There should be another 63 here because we divided by 3. So this should give us the points that we need. Oh, I see it, because we only need these. We actually don't need this one, because if you add these up, what you end up with is always going to be 45. So we don't really need that 45. I'm going to show you what I mean. What I want to do is create that list that I just made, that scribbled, starting with the 45. So I'm going to do a merge. I'm going to merge that one first, because in the end, and I'm going to do a mass addition in order to show you what I'm doing. Mass addition from that, mass addition of 45 to 45. But observe what happens when I insert. Should I use this one? So I need this value to be total of 280, or whatever the total length is of our bridge. But so that means you can start adding it by doing actually this. Actually, yeah. But do I need this then? Okay, then I come close to 280. This is one way you can do this. What you can also do is just use the repeat, the repeat data. The list you want to modify is just this one, and the amount, well, it's 3. So you can just plug that one in there and get rid of all these duplicates. Let's flatten this once more. And then you get, oh, I think I'm forgetting the last one. So let's plug that one in here also. And what I want to do with this, I want to remap this into 0 to 1, because I always like to have these unitized domains. So I'm going to do a bound. Actually, no. I'm just going to use my total length as the source of the domain. And the values I want to remap are these. And what I will get, actually, I have to use that value instead, because this is the total. I'm not remapping the same value, because that will give me the wrong values. But what I want to remap is not the overall addition, but the incremental addition. But I can always see there's a, okay, so it's sorted. This is another reason to explain to you about the differences, that sometimes you would use the merge, and sometimes I would like to use the entwine. The entwine doesn't mess up your ordering of points, because if you see here, if I flatten that part, right, you will see that 45 is now the second, even though I put it in the third in the last place. So if you were to do the same with an entwine and then flatten that entwine, you will see the difference between the ordering of points that it kept. So I'm gonna go here and then flatten the end. You see the ordering is exactly how I expect it to be, but the merge, it actually sorted that, pre-sorted our numerical values, which I don't want in this case. So I'm going to replace all that with this here, and this would give me a incremental increase that closer to that 280, 99. I'll take that. So I'm gonna use that as the points, as a value to remap. This is one of the reasons why I was actually reluctant to include the last 45, because if you evaluate a curve at this point, well, you're just going to be at the end, which is not really what I want, okay? Because in the end, there's no column. So I'm just going to remove that one. And I have 4 values, which equals to the 4 columns that we will have. The last one is always going to be the same, because we subtracted that first before divided this middle section. So that's going to be fine. And what I'm going to do is actually do this here and come here and say CRV evaluation. CRV evaluation on the curve that we moved, which is this one. We can reparameterize it, which is the whole reason why we did all this. And I can't delete that actually. And then take this. What I achieve with this is actually on the curve, I can now see where the columns is going to will be roughly situated. So that point, this green point, and that green point. I do think that the video has become very long now, so um, I will put the next part in the next video so we can continue from there. Start with a fresh mind perhaps, which always helps. But what I'm going to do is in the next part, I will try to use the information that we've created for ourselves here, here. So these points, find a way to extract the neighbor points, right? So we can create our, oh, that one is messed up. But anyway, you know what I mean, is create that part and create this part. We've done the legwork in this part, so hopefully in the next part, it's going to be more fun into creating actual geometry instead of setting up the preparation for it. So that's going to be exciting. With that said, I'll stop the video here and I'll see you in the next part.